Hey everyone, thanks for sticking around to the apparently the last talk of the day. So I appreciate your attention. Oh, that's okay. Thank you. My name's Glenn. I work for a company called Vast Data, but I'm here to talk about Ray, and I think that's why we're all here. And so, as hopefully all of you know, Ray lies at the heart of scalable AI workflows. It's the magic that takes, what you develop on your laptop and deploy it out and scale it up and do amazing things at scale. But it was built with this assumption that compute is smart and can be orchestrated intelligently and scalable and all these wonderful things, but storage and persistent data is over there somewhere, not to really be talked about or touched or relied upon for anything except the most basic of needs. And the company that I work for, Vast Data, we're building a AI operating system, as we call it, that challenges that assumptions. And so a little bit of what I'll talk about is what's within the art of the possible when you have a data plane to complement what Ray does on the compute plane to create a more responsive AI platform that shares the same great qualities of Ray, but on the data plane side. So Ray doesn't need any introduction, of course, but when I said Ray treats data as this other thing, let's talk about that for a second. And so, Ray lets you scale up, things on your laptop to things that run over thousands or tens of thousands of GPUs. And it has this great ability to react to changes in the environment, right? So as workloads change or as resources change, AI workflows can respond accordingly. But it treats data, like I said, as this other thing, right? I think Thanksgiving's coming up, and I think of this like Ray is at the adults table, and data sits over at the kids table. And while the adults are having adult conversations and doing amazing things, the data is given only very basic directions. Hold on to this stuff, don't lose it. Give me it back when I ask for it. And if I need anything else from you, I'll let you know. And so in practice, when Ray workflows have to interact with data, you have a bunch of essentially nagging, right? Like you have all of the workflows have to just constantly, ask the storage, has anything changed? Do I need to do anything? And this model has worked fine in the days prior to, the big explosion of Gen AI. But as workflows scale up and data scales up, there's now this mismatch where Ray has kept up on the compute side, but data is still treated like this very primitive thing. And so what we've done at Vast Data is take the ideas and the things that make Ray great for compute and create a data plane that impedance matches what Ray does for compute, but for data. And so what we do at an infrastructure level is we have two layers, just like Ray has compute and persistent data. We also have compute and persistent data. And so at the top here is our compute layer. It is stateless. It scales out linearly. It's a bunch of VMs or containers running, and they can expand and contract, and they contain no state. And what we do is deploy data services on those resources. Underneath that is what we call the element store. And to a first approximation, this is just thousands and thousands of SSDs. And they are connected to our stateless compute layer through a high-performance fabric. But when you hook things up this way, we call it the disaggregated shared everything architecture. We can enable a bunch of rich data services that look and feel like a storage system, but can also be much more reactive and responsive and elastic, much like Ray is. And so, for example, the first data services that we exposed to our customers in our layer up here were NFS and S3 services. And so you can talk to the Vast AI OS through NFS and tell it, store this data, and that data gets stored, just like you would expect from any scalable storage system. And we have all of the good things that one would expect from an AI-ready storage system. And so our namespaces in production exceed an exabyte now. And we can, we deliver the full benefits of all flash at that scale through these interfaces like S3 and NFS, but that's not the only thing we do. And so because we're just running stateless services that express the data that's stored in our element store as files or as S3 objects, we can also express that data in much more meaningful ways that are much more semantically aligned with the needs of a Ray workflow. And so, for example, you could insert data into the vast AIOS using SQL inserts, using something like Trino. And then if you look at that same data through the S3 interface, it appears as a Parquet file, and you can interact with it as if it were a Parquet file. But under the hood, it's being represented in our native format under here, and it can simply be expressed as Parquet or as rows or columns in a database. Similarly, we also expose out an event API, and so you can react to events that are happening within the data system. And we also expose, for example, a vector search API. So rather than, so let's now talk about what happens when you plug, such a responsive and flexible data platform or data plane into the flexible and responsive compute plane. Suddenly, Ray's orchestration layer is not the only thing that can call the shots. It's not the only thing at the adult table. Now the data itself has agency and can emit events that can kick off Ray workflows. And so now both Ray and your data that Ray operates on can be reactive and responsive to each other. And just as Ray scales out to tens of thousands of GPUs, the data can scale out to exabytes of data under a single namespace and terabytes per second of performance, or equivalently, trillions of vectors or hundreds of millions of events per second if you interact with the data through those interfaces. And so these are all features, but now let's talk about what you can actually do with this. And so the canonical pipeline that one might, the first thing you look at if you open up the Ray manual or user guide and look for examples is RAG. And this is something that's very popular amongst our customers because we provide very robust support for scalable RAG. So, without VAST underneath Ray, you might implement RAG in a way that looks like this. And so you have S3 storage and data is coming into it. And then it's up to something running somewhere to constantly ask S3, hey, has anything new shown up? Hey, has anything new shown up? And so again, it's, like adults nagging their children, hey, has anything changed? And so in practice, this might be something as simple as a cron job running in a VM, or it could be something handled by something more complicated like Airflow. But when it detects something has changed, then it is up to whatever that detection mechanism is to kick off a Ray task. And this now gets into where Ray shines, right? And so the data can be chunked in a scalable way, and it can be embedded, and then those embeddings have to go somewhere. Where do they go? Well, you have to deploy a vector database so that those vectors are then searchable. And so, Chroma is a fine example of a scalable vector store, but choose your favorite one to insert here. And so at the end of the day, because Ray treats storage as a dumb thing, you wind up having a whole bunch of parts that have to glue all of this together on the data plane, even though Ray does a fine job of orchestrating the compute side of it. This adds complexity, this adds fragility, and it adds human overhead. Now, if you were to deploy the same pipeline using Ray on top of the vast AI operating system, things look a lot simpler. And so just as you inserted or you uploaded data to an S3 bucket before, you upload data into VAST using an S3 API. But because VAST is reactive, it has to react internally whenever a new S3 object is uploaded anyway. I mean, that's how it makes the object appear finished and show it in the S3 bucket namespace. But because we express those events that happen internally, externally through a Kafka-compatible API, anyone can subscribe to the events that say, hey, data has recently arrived through S3. And so you can run something that subscribes to the event broker that is internal to VAST, and you can react to cases when new objects arrive in your bucket. Then you kick off Ray, just as you did before. It does what it does great. It chunks up that data, it generates embeddings. But instead of having to shove those embeddings in a secondary vector data store, you can then shove those vectors right back into VAST. And the way this is done is those vectors can be stored as object metadata on the S3 objects that were used to generate them. But because we store S3 metadata internally, not as S3 metadata, but in a tabular format that can be expressed as S3 metadata, you can also run vector queries against that same metadata. And so suddenly you have your vectors, you have your objects, and you have the eventing infrastructure that allows Ray to react to new data arriving, all sitting under a single intelligent data plane. And one really nice aspect of having all of this data consolidated under a single pane is that because we represent this data in a single place, it's not like we are slapping a Kafka broker on top of a storage system or a vector database on top of a storage system. Those are just ways to express the data that's already there. And so as soon as you change, for example, the permissions on the object that was uploaded here, because the vectors are represented as object metadata, the permissions are automatically carried forward to all the object metadata, and therefore those vectors instantly have the updated permissions. And so if you need to revoke access for certain objects, the second you do that, you can no longer find those objects when you issue vector queries as well. And it's not like we have to do any synchronization. It's just a reflection of the fact that that data is stored in a single way under the hood, and we're just expressing it out through a bunch of different ways. I've only got a few more minutes, and so I'll skip ahead and let you all go a little early. Another example that I had was a little more complicated that relies on the fact that we also have a transactional database. And so you can do row-wise ACID-compliant inserts. And then under the hood, we repackage that data asynchronously into columns. And so when you query that data, it gets columnar store performance and scalability. And because of the way we architected this distributed shared everything architecture, there is no partitioning. There's only one partition, but you get the full performance of every SSD that data lives on. Skipping ahead. So wrapping it up, I hopefully have imparted that Ray does amazing things on the compute side, but it has long suffered storage systems that simply offer no intelligence that Ray can act upon. And the result is adults at the adult table treating data like kids at the kids table. And what we've done at VAST is impedance match what Ray can do on the compute side and provide an equally scalable, expressive, and reactive way for data to be stored so that Ray can react to data changing just as much as Ray can cause data to change. And the combined net of that is that everything can now be run more efficiently with less complexity, better scalability, and the world is a better place. Thank you for your attention.